Hello.
Hello.
Hi.
Yes, fine. And
Again.
I also have oh,
You also have what?
YouTube stream.
Okay.
And I send the link to you if you want to. Oh.
Yeah, so but I saw your face talking, but I saw your face.
What? I cannot connect to.
I think now you have to do it by this application. You have to download Airtime.
Blast. Okay. Yeah, right now.
What?
Okay, yes, I should also share the. Huh? Now I'm sharing the screen.
Let me check. Maybe can you talk to see if,
Yeah. Thank you for coming to my defense. I'm Mulin from the teaching team at keep talking about
yeah. And we said that so now it's good.
okay at University of Antipolis.
Okay. Let's stop. I will stop that and we'll start.
So you connect by the link I sent you.
Yeah, I just click on the link and it's working. You have a delay of 30 seconds.
Oh yeah, just normal. So.
Just 2 seconds. Okay, so I will take the time. Okay, let's go.
Thank you for coming to my defense. I'm Mulin from teaching team at University of Antipolis. I worked on my thesis under the supervision of Professor from Han Lapak. Today is my pleasure to present to you my thesis, reconstructing and repairing urban models with kinetic data structure. Urban digital twin is gaining more and more attention. It has many applications. For example, intelligent urban management and planning, interactive designing and energy analysis. The application scenarios can be roughly separated into two scales, city scale and building scale. In these two scales, GIS and BIM are proposed as tools to realize urban digital twin by comprehending and maintaining the 3D virtual models. Therefore, the fundament of urban digital twin is the models. In this thesis, the goal is getting valid virtual models which are free of geometric and topological errors and can be directly used by some downstream applications. To investigate this problem, let's first see how the 3D models are formalized in GIM and BIM systems and how they are generated. So firstly, in the city scale, the most used data format of GIS is the CityGML. In addition to the geometry of urban objects, it can also record the topology, semantics, and appearance. Specifically, CityGML can present an object in different levels of detail. Among them, LOD2 is widely used. It presents the buildings here, the buildings by their enveloped surfaces, where the thickness of structural elements are ignored. So we call them surface-based models. In the building scale, IFC is widely used to describe only one building in detail. It includes additional information such as the project budget and schedule, in addition to geometry, topology, and semantics. Different from CityGML, IFC models consider the thickness and the present buildings with IFC elements, like this one. And each IFC element is a semantized volume. So IFC is a volume-based model. To obtain this kind of 3D models, there are typically two ways. First, 3D models are designed and created by architects or designers using specific modeling software such as Revit. However, some errors can be easily introduced into the 3D models, such as self-intersection, vortex misalignment, missing facet, overlapping, wrong orientation, and gap. These errors make the models cannot be directly used by some downstream applications, such as energy analysis. Automatically reconstructing 3D models from data measurement, like point clouds, is another generation way. However, there is still a long way to go before automatically reconstructing semantic enriched FC and CTGML models. Therefore, researchers attempt to first automatically reconstruct compact and editable CAD style models, like compact mesh. However, this is still an ongoing topic. A more efficient, robust, and scalable reconstruction method is desired. Regarding to the two model generation ways, this thesis explores the problem of getting valid models by repairing existing defect-laden 3D models and efficiently reconstruct compact meshes from 3D point clouds. Overall, repairing and reconstructing 3D models are difficult. They pose several scientific challenges. For repairing, the first challenge is to deal with both surface-based and volume-based models. The next challenge is to deal with different types of geometric and topological defects. The last challenge of repairing is to deal with the ambiguity of semantic errors. Semantic errors are sometimes subject to interpretation. For instance, the error in the red dash circle can be both floor or wall. For reconstructing, the first challenge is to deal with point clouds that are obtained by different acquisition systems and are used to present different types of scenes, like outdoor scenes or indoor scenes. Another challenge is scalability. The size of obtained point clouds are typically quite large due to the characteristics of urban scenes. The last challenge is how to choose quality metrics. Different criteria might be considered in various applications. For instance, heritage recording attempts to reconstruct as many details of an object as possible, while SLAM always overlooks details in order to reconstruct a scene in real time. Therefore, the reconstruction method should have the capacity to trade off between several considered criteria. In the rest of my presentation, I will introduce our contribution on compact mesh reconstruction that relies on improvement of two key ingredients of kinetic sub-reconstruction method, and the contribution on repairing 3D urban models. For the compact mesh reconstruction part, to begin with, let us briefly summarize the existing methods. We separate them into three families. The first family is the simplification method. Compact meshes are simplified from dense meshes by clustering techniques or edge collapse. Another family analyzes the connectivity relations between planar primitives extracted from point clouds and reconstructs the compact meshes by closing the gaps. Also, departing from planar primitives extracted from point clouds, partitioning-based methods divide the 3D space into a set of polyhedron cells, and mesh surfaces are extracted by labeling each cell or each polygon. Among them, kinetic shape reconstruction method is efficient, scalable, and robust. Planar shapes that are first detected from the input point cloth, then extend the convex hull them until they collide with each other in a kinetic simulation. This operation decomposes the bounding box of the object into a small number of polyhedron, from which the polygon mesh is extracted as the final compact mesh. Among the three steps, kinetic partitioning is the core part of this algorithm. In the paper of Boucher, 4 possible collision cases are well defined, and an efficient exploration mechanism is designed to iteratively maintaining the collision events and updating the kinetic data structure. However, the rest 2 parts can still be improved. Like in KSR, incremental mechanism, like region growing or ransack, is used to detect planar primitives. They cannot find good planar primitives and lead to a bad reconstructed mesh. The mesh surfaces are extracted by predicting the semantic level for each polyhedral cell in the kinetic data structure. This problem is solved by minimizing an energy function, and the fidelity term of this function is formulated based on the oriented normal of input points. However, oriented normal is not easy to get in real world. In the following of this section, I will present how to detect good planar primitives, good planar primitive configurations from point cloth, and how to extract surfaces without the requirement for oriented normal. First, a better planar primitive detection method. Detecting planar primitives from 3D point cloth is a long-standing problem. It consists in grouping input points into clusters while associating a parameter plan to each of them. Two user-specified parameters control the precision of the output configuration, as fitting tolerance epsilon and a minimal primitive size sigma. Solving this problem is not trivial, as the number of primitives is unknown and some input points called outliers are associated with no primitive, as they do not fall in the fitting tolerance zones of the primitives. Next, let's consider what are the characteristics of good planar primitive configurations. It should have high fidelity. We prefer the left one since it has a smaller distance error between primitives and inliers. It should also be simple. The left one is better here since it contains fewer primitives. It should finally have a high ratio of inliers. The left one is more complete since it contains less outliers. Somehow, finding a good configuration turns out to be a trade-off between the 3 objectives. It's, however, difficult to find a good configuration because the solution lives in a large mixed, discrete, and continuous configuration space, which contains a continuum plan parameters estimation space and a discrete point assignment space. In addition, the dimension of the space is variable since the number of primitives is unknown. Several families of methods have been designed to solve this problem. The incremental mechanism, such as region growing or ransack, detect primitives in an iterative manner by using local planar hypotheses. Energy-based model typically generates a set of planar hypotheses before assign one of them to each input point using a multi-labeling energy minimization. Learning-based approach predicts point pointwise feature before it's meeting the primitive types and parameters. And here are also some methods designed to enforce the geometric regularities between planes. But none of them can seek for the three objectives simultaneously, and none of them can operate in the whole solution space. For solving that, we propose a sample and natural energy function with respect to the three objectives, and an exploration mechanism which uses file operators to modify a configuration guided by this energy function. For the energy function part, it measures the quality of primitive planar primitive configuration X, which consists of a set of supporting plane parameters and the assignment of input points. The energy function has three terms. Each of them is corresponding to one of the objectives: fidelity term, simplicity term, and the completeness term. The fidelity term is related to the average Euclidean distance between the primitives and their inlayers. Note that other metrics can be also considered, such as the normal deviation between the primitives and their inlayers. The simplicity term is the ratio of the number of detected primitives to the maximum primitive number. Completeness term is the ratio of inlayers. And all the three terms are in the interval between 0 and 1. There are also three weights: omega f, omega s, and omega c. They can balance these three terms. For instance, when we increase the omega s, we can obtain a concise, compact configuration. Now I will introduce the exploration mechanism beginning from operators. Transfer operator transfers the inlayers between pairs of adjacent primitives. It first assigns the inlayers in the adjacent area to a closer primitive. Then the primitives are updated according to the new groups of inlayers. We keep doing these two steps until there is no more inlayers can be assigned to new primitives. Merging operator merges two adjacent primitives together and assigns faraway inlayers to outliers. Splitting operator splits one primitive to two. We first find the farthest inlayer on each side of the primitive. The other points are then associated with one of them by special proximity. Finally, the transfer operator is used to refine these two groups. Exclusion operator excludes k farthest inlayers to outliers. Insert and finally, the insertion operators insert the k closest outliers to inlayer. These five operators are guided by the energy function through a priority queue. The priority queue assigns the highest priority to the operation which decreases the energy the most. We keep implement the first operation and updating the priority queue until there is no more operation can reduce the energy. By observing, we found that our method is slow because transfer operator is called too many times in the priority queue. We therefore speed up our method by using a global transfer operator outside the priority queue, which transfers inlayers between all the pairs of adjacent primitives simultaneously. The exploration mechanism now is alternating between the priority queue and the global transfer operator. And here I show the energy evolution. This green curve presents the speed up mechanism, and the orange one is the original exploration mechanism. For the blue one, it is non-local simulated annealing method. We can see our speed up exploration mechanism can convert to almost the same energy, but with much less iteration. The algorithm departs by initializing a primitive configuration, then iteratively modifies the configuration locally and globally until there is no more operation that can reduce its energy. Okay, and now let's see some experiments. We first show the result on different acquisition methods: CAD sampled model, laser scan, and MVS model. Our method is robust enough to handle all of them. We then compared the algorithm to two families of existing methods: the incremental mechanism, region growing, sorting region growing, and ransack on a sensitive ABC dataset and the real-world PSR dataset. We also compared it with learning-based approaches, SPFN, PassNet, and HPNet, on two datasets which only contain planar piecewise models. We can see our method competes well. And here is a virtual comparison with region growing and ransack. We can see our method can detect meaningful and concise configurations with smaller distance errors, fewer primitives, and more inlayers. And in this noted part, we can see our method can detect the meaningful chairs. And the comparison with learning-based method on smaller scale point clouds, SPFN can detect plenty of outliers, and the PassNet, HPNet cannot separate the closed parallel primitives. Instead of using region growing in KSR, our method can lead to better reconstructed compact meshes. In particularly, the shape of output polygonal facets adapt to the local surface geometry in coherence with the prediction of the Dubin indicatrix. And here we show more reconstructed results on complicated free-form models, and on large-scale urban sense models and indoor sense models. We can also generate the reconstructed compact mesh at different levels of details by progressively decreasing the two parameters, sigma and epsilon. Note that the proposed method is flexible enough to introduce other objectives. Here, I demonstrate the extensibility of our method by introducing geometric regularizations as a fourth objective. Here we consider parallel, orthogonal, and coplanar as geometric regularization. We introduce degree of freedom to qualify the geometric regularity of a planar shape configuration. As we can see from this figure, the degrees of freedom of configuration is smaller and smaller when this configuration is more and more regular. For the regularity operator, instead operating on a single primitive or a pair of adjacent primitives, it operates on a regularity graph, which contains all the regular relations in the configuration and built by progressively detecting nearly parallel, nearly orthogonal, and nearly coplanar primitives. The regular relations are not independent and complicated. Therefore, we introduce a constraint to simplify the solution space. We consider that the regularity operator can only operate on a subgraph induced on the regularity graph by a random node and its adjacent node. For instance, this subgraph 3 is induced by this green point node and its two adjacent nodes. This green one, this blue one, and this yellow one. Given an induced subgraph, we regularize the related primitives by repositioning them to be exactly parallel, exactly orthogonal, or exactly coplanar. The extended version can lead to more regular configurations. The parallels and parallels, orthogonal, and coplanar primitives are in the same color. The regularized configurations can lead to more compact meshes with fewer facets. Next, I will present a more practical way to extract mesh surfaces from the kinetic data structure. POCO is an efficient implicit neural network. It predicts point-wise latent vectors for each input point before computing latent vectors of the given query points using learning-based interpolation. The query point features are finally decoded to occupancy probabilities. This method can directly predict the occupancy information from point coordinates. We therefore adapt POCO in KSR. From a point cloud, we can get a kinetic data structure using planar shape detection and kinetic partitioning. We can also get a set of query points and their predicted occupancies using POCO. The predicted occupancy information can be used to reconstruct the fidelity term of the energy function. Intuitively, a polyhedron cell has more chance to have the same semantic class with its inner query point. Finally, the surfaces are also extracted by minimizing this energy function. Here, we compared our method with KSR on ABC dataset. Fidelity and simplicity are considered as measurements here. We can see KSR reconstructs more accurate meshes, while ours reconstructed more compact meshes. It is hard to definitively state which one is better. However, the measurement is essentially the same, and ours does not have the limitation of normal orientation. Therefore, the new pipeline is more practical on such sensitive data. We then compared them on different freeform and man-made objects. For the clean points clause, ours can reconstruct the meshes with almost the same quality as KSR, since POCO is trained on this kind of clean point clause. In addition, our approach cannot reconstruct as good results as KSR on noisy and complicated point clouds, like the cross. To conclude this part, I propose an efficient planar shape detection algorithm, which relies upon a simple and the natural energy function and an efficient optimization mechanism. It is flexible and robust on different types of sense and acquisition system. In addition, it's extensible. Note that this detection method is independent and can be used for other applications. And I try to adapt and implement neural network into KSR for making the pipeline more practical and be free from the constraint or requirement for oriented normal. Now we arrive at the repairing part. Let's also start with the prior work or existing work. There is only few prior work on FC repairing. One detects the frequented geometric error in FC models and semi-automatically corrects them by local operations. Diakity builds the topological relations of elements using a space partitioning data structure. For CTGML, a few work repairs CTGML models by detecting and correcting errors locally, like this one. And Zhao proposed a global repairing method by carving tetrahedralization and topological and geometric constraints. However, there is not a general and robust repairing methods that can repair both FC and CTGML models. And none of them can guarantee the validation of the output. By observing defect lesion urban models, we found out the geometric and topological errors are almost caused by erroneous connections between adjacent facets. To correct them, one way is to rebuild all the connection of the input facets, and this can be done by constructing a kinetic data structure. Our algorithm departs from an urban 3D model here, an FC model with errors. A super disconnected semantics or original facets are first extracted from the input model. They are then simplified to a set of primitives and are taken as input of the kinetic partitioning method. The primitives are extended until colliding with each other and divide the 3D space into polyhedron cells. Finally, these polyhedron cells are labeled with semantic classes by minimizing an energy function. And a corrected model could be easily extracted. Now let's see them step by step. Disconnected facets are first disassembled from the input models and are enriched with semantic classes. The semantic classes are actually associated with space in the input model. We should propagate the semantic classes from space to facets. Because the normal of each input facet points towards outside space in case of CTGML, and towards the center of its FC element in case of FC model. We therefore consider a facet has the same semantic class as the space pointed by its norm. We then regroup coplanar facets and extract their convexor as primitive. These primitives are then grown at constant speed until colliding with each other and decompose the 3D space into cells. We assume that the corrected model is a combination of some polyhedron cells in the kinetic data structure. For extracting them, we should assign semantic class for each polyhedron cell. We formulate this problem as multi-labeling energy minimization. The energy function has a fidelity term and a complexity term. The fidelity term measures the consistency between the semantic class assigned to the polyhedron cells and the semantic classes of the input facets. More precisely. For each polygonal facet F of each polyhedron cell I, we find all the input facets that are coplanar with F and point towards the center of I. The cell I likely has the same semantic class as this input facet, weighted by the overlapping area. The complexity term handles configurations that are either geometrically complex or semantically improbable. W is a metric to consider the nature of two connected elements. We also have a parameter lambda balancing these two terms. Here is the impact of the lambda when only fidelity term is taken into account. Lambda is 0. Polyhedron cells are mislabeled at several locations. Our complexity term allows the correction of such misalignments. When we improve lambda to 0.5, but given too much importance to the complexity term can, however, oversimplify the labeling. In addition, when considering a standard pose model with a binary matrix W, some unrealistic configuration can appear. We then evaluate our algorithm. First, on LD2 CTGML models. Here is 100 buildings in HANOVA dataset. We obtain 300 defect-laden models by introducing errors into this 100 model. Our method can repair more than 97% defect-laden models. However, here, and note that here we use Watts-Ridici as the evaluation tool. And we also show two examples. These two facets contains missing facets and the misalignment, misalignment errors. Our method can fix the errors and output a watertight and manifold result. We also compared with HSW method on two real-world CTGML datasets. Our method achieves better repairing results compared to HSW. We also compared with 3 generic mesh repairing methods. Only our method can correctly repair the 4 input models without remaining errors and keep the subfeatures. We then tested our algorithm on FC models. Because there is no tools available to test the validity of FC model, we proposed several criteria here to check whether an FC model contains some obvious geometric or semantic errors. We tested our method on FC models given by an FC expert that's different in terms of complexity and levels of detail. Input defects such as overlapping and gap are fixed even for complex buildings in a reasonable time. However, our method cannot correct all the semantic errors because semantic in FC model are sometimes subject to interpretation. Therefore, it can be interesting to provide to the user a confidence score on the semantic class associated with each polyhedron cell. User can quickly check the cells with small confidence and change the wrong semantic classes. The confidence score can be the value of fidelity term of the entry function. And here I show a video to present a designed interface. From an input FC model, we first disassemble the input model, then extract the primitive. The kinetic data structure is then built and each polyhedron cell is labeled. We then We then find the cells with low confidence
Okay, keep going.
confidence score. After checking, we find that it should be wall and misassigned to be space. We then correct it and correct it using its index, and the semantic error can be corrected. To conclude this part, I propose an automatic approach for repairing geometric errors contained in urban models. It can adapt to different types of urbans like CGML and FC. It's robust to different types of errors, and it can also offer the confidence scores to help user interactively correct the wrong semantic labels. Now I will finish my presentation with a conclusion. I investigated the problem of repairing and reconstructing 3D urban models. On the reconstructing part, I first proposed a better primitive detection method. Then I tried to combine classical compact mesh reconstruction method and implement an implicit neural network to make the reconstruction pipeline more practical. On the repairing parts, I propose a global and general approach for repairing different types of geometric and topological errors contained in common urban models. Next, I will then let's see some of the limitations of our method. First, the planar primitive detection method needs long processing time on large scale point cloud, and our detection method needs a good initialization. As seen, departing from good initialization given by Ransack and region growing, our method can converge to a better result. And the proposed surface extraction method cannot extract good results when there are large missing parts in point cloud due to the limitation of POCO. The repairing method can also fail when the input mesh is highly non-manifold or too many facets are missing in the input mesh. As mentioned previously, the repairing method cannot correct all the semantic errors. In addition, a better evaluation tool is required for FC models. And then I will talk about some perspectives. First of all, separating a large point cloud into several semantically consistent parts and conducting the optimization of each part in parallel would be a good way to reduce the running time. Secondly, the shape detection method only work on planar primitive. A straightforward extension of this work would be to support more complex objects, including sphere, cone, cylinder, or even nerves. It can lead to simpler and more accurate configuration. Moreover, a graph neural network could be a good choice for predicting the semantic class of each polyhedron cell in kinetic data structure. While training the network requires an enriched training dataset. In addition, an ideal urban data twin can control and manage the city in both city scale and building scale. Therefore, creating a multi-scale urban data twin is a good future research direction. One way could be creating an integration of BIM and JS. Finally, I think that classical geometric processing and deep learning have advances in different applications. For instance, deep learning is good at segmentation and detection, while geometric processing is good at generation and reconstruction. In my opinion, designing end-to-end deep learning methods to deal with all the geometric problems is not efficient, and combining the classical geometric processing and deep learning in an efficient manner would be a more interesting direction for future work. Thank you.
Okay, it's 43 minutes and a half. So your last sentence was well good, where you give your opinion on that. Yeah. Okay, so I will tell you about what's not going. So first, you haven't done the presentation for the defense or for defense. It's not a PhD defense presentation.
Okay.
It's an engineer presentation. You presented the algorithm you designed. There is no the scientific way, the observation you had, and the things you try, and things like that. Just too straightforward. Okay, so I told you that when we give you some examples, but when you talk about preparing method and you say you have to talk about the defect, then you have to say, yeah, we observe that all these defects, there is a common point. It's come from facets, the problem of connection between facets. Okay. And one way to potentially fix this error, instead of try to identify specific error and then correct it with a specific way. One way, a general way to fix all this issue, is to rebuild the connection. You have to explain that. It's come from observation, and you think that you have the idea of doing that. It's the key part. This argumentation and this slide should be the most important slide of the repairing method. Okay, so you really have to work on that. So, okay, let's come back at the beginning. Okay, other things, it's a trial today, but today, your presentation, it's amazingly boring. You read, you don't look at me, you read. So if you put the amplitude of your voice, it's doing that. Blah 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 blah. Then blank. We are the button. Blah 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 blah. During 45 minutes. So you will have to practice that. You will have to look at people. You will have to do intonation like that, and we have that, and blah 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 blah. You have to become somehow an actor, because here people will see.
Okay.
Okay. They will see. They will see. Okay. So you will have to practice to have intonation. You will have to not read the sentence. You have to learn the sentence so that you even don't look at them.
No cost.
If you cannot do that, remove your sentence and learn them and interact like that. Okay. Because sometimes, when you write your text and things like that, you have the feeling you have to read it, and you're less good at presenting. Because when you don't have the sentence, you interact more with people and things like that. So I don't know, but here it's fun. Okay. So I think globally speaking, there are too much slides. You have to reduce. We have to remove some parts or go very quickly on some parts. You can, for instance, for POCO or the regularization, you can go more quickly on maybe the regularization. You say it, I say we also did that, just one slide. We also work on that for regularizing the primitive. The idea is to add a new term and blah, blah, blah. And you show a few results. And say, I will not go too much into detail because of time constraints.
Okay.
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 Then you talk about, because here you have plenty of slides that where it does not go. It's not well because you have many information on the slide and